Welcome you all to this course on defects in material. Okay. Today we will have discussion on interfaces in material. Even if we consider any material as perfect, even if it is a single crystal, one defect which cannot be avoided is the surface. Why do we consider surface as a defect? Because at the surface, if you look at that material, at any material, that's the surface is a discontinuity. That is, if you look at atoms inside the sample, where the number of identical atom positions which are available, if you look at the surface, some bonds are broken. Okay. So that means that when a surface is created, a material without a surface and with a surface, there is some energy which is required to generate the surface because some bonds have to be broken. So this is an excess energy which is required, correct? And this energy which is required or the energy which is available to the surface, or the surface energy is called as the surface energy, that is per unit area. Okay. This is what we use as gamma, the surface energy. So that means that if you have a sample, that sample could be been made vapor to solid or liquid to solid, or it could be these type of interfaces could be between solid and solid as well. Most of the materials which we use, okay, the solid to solid interfaces, which is very important, okay, that will come to later. But essentially it does not matter what is the method by which we are making a solid sample, okay, an interface is invariably created. Okay. Even in a single crystal, that interface will be there. So what will be the free energy of that sample if we consider? That free energy will be, the total free energy depends upon G0 plus gamma into A. A is the total surface area, gamma is the surface energy, G is the bulk chemical free energy. Okay. If you look at this expression, okay, how can we calculate this surface energy? Okay. Is there any experimental way in which it could be measured? One can think of a way in which a thought experiment which we can do it is, you take a wire of a sample, you apply some load, try to pull it. Then when we do, there is going to be an increase in area which is going to take place, right? So the total energy which we are putting into that sample is F into, suppose dA is there, F into dA becomes the total energy increase. Okay. If this energy is just sufficient, assume that to balance the new surface which is being created. Okay. It is not doing anything else other than just to balance that surface energy. Okay. So to create the surface, some requires some free energy. Okay. So how we can calculate it? If we take this differentiate, this will be equal to gamma into dA, A into d gamma, right? This is the change in, it is just balancing this. Then we can write this to be equal to F into dA, correct? Or we can write F can be equal to gamma plus A into d gamma by dA. This is how this expression. So, this is nothing but the force, okay, and gamma is the surface energy. Okay. This is the rate at which the surface energy changes multiplied by the area. This is how the force will be varying. Suppose we assume that it is from the liquid to, in a liquid if we consider it, then what is going to happen is that in a liquid the surface energy is independent of the area, correct. So, this term will turn out to be 0. So, this will become F will be equal to gamma. Then in this case we can consider this as a surface tension, right. The force when it is a surface tension and surface energy, the same can be used. But in the case of solid samples, okay, we cannot assume that they are the same, because when we take a sample, a liquid film, and try to increase its area, quickly the atom molecules rearrange themselves so that the surface is created. In a material, solid material, if you try to pull it and the atoms have to rearrange on the surface, it may be taking a finite time, okay. So, if the experiment is being done, okay, is very slow, the time which it takes, experiment is done in a fast time, but the time it takes for rearrangement to be, in such cases the surface tension or the surface force need not be the same as the surface energy. Is it clear? That is because this term is not going to be equal to 0, okay, because there are viscous forces are going to be there, okay, it is highly viscous, the sample is. Okay. If you wanted to find out the surface energy of a specific surface, what is the way in which theoretically we can try to find out in a very simple way is essentially see how many bonds have to be broken to generate that surface, correct. Here in this particular case, in FCC lab, there are 3 types of surfaces which are being considered, okay. That is with low index plane, 111, 100 or 110 type of surfaces, okay. 111 in FCC is the close packed surface. In this case, if an atom is sitting at, for this atom if we consider it, the nearest neighbors which should have been there if another layer is there on top of it would have been 1, 2, 3 atom positions it would have occupied. So, these 3 types of bonds have been broken compared to total coordination which is going to be there, correct. With respect to an atom, if you consider in a close packed direction, there are 12 are there, out of which 3 are getting broken. So, if you know what is the bond energy for each type of a bond, then we can find out what is going to be the surface energy, correct. That is what essentially is given by this formula. This is E, this is solid to vapor, N, where N is the number of bonds which are broken bonds, okay. So, that means that depending upon the L is the latent heat of sublimation for the atom to sublime from the surface, which we assume it to be a constant for the material. So, that means that depending upon the number of bonds to be broken, which is going to change depending upon the nature of the surface, okay, the surface energy will change, correct. Close packed plane will have the lowest surface energy. Okay. Is this clear? Okay. Then this energy which we talk about is the surface energy. This surface energy is not the same as the free energy of the surface. The free energy, when we write plus PV minus TS, correct? This is how to write it. So, if PV is constant, then essentially E is the surface TS. So, TS is where that entropy term comes into the picture. In the case of a surface, the entropy term, because lots of bonds are getting broken, atoms will be moved from their positions. So, the contribution of entropy is going to be high, and that is going to change from surface to surface, and in addition to it, lot of defects could be produced on the surface. Okay. So, when we try to calculate what is going to be the free energy of the surface, that can vary, okay, from surface to surface. Here in this table, what is being given is the surface energy which has been calculated close to melting point, okay, for different type of samples. Okay. And the cases which we have considered so far, what we have done, we have looked at close packed planes or low index planes which we have considered it. And when we look at surfaces, two things which we have to consider. One, not only the energy of the surface, and another is the structure of the surface. The structure part of it we will come later, but now we are essentially trying to concentrate on the energy of the surface. Okay. Suppose we wanted to find out what is going to be the surface energy. Okay. It is a high index plane. That is, we have so far we have considered with respect to 1-on-1, which we have considered 3 type of surfaces we looked at it. But we can look at any surface which we can take, any cut section can be a surface. It could be a high index plane. So, how do we find out the surface energy? From values which are known for low index plane. The method which is adopted, this is what is called as a broken bond model, where you look at this surface. Here, this is the simple cubes which are joined together. The bonds are broken at different places. Okay. What we are considering it is essentially any surface which we can consider it, a random surface, could be considered as creating some steps on the sample surface, right. That is, suppose a surface which is going to be there, low index one is the one which has got the minimum free energy, right. So, that is the one which you try to have. So, with steps, if we try to create surface like this, the average, if you look at each of this surface, this will be a low index, only some step is being created. Okay. That means that closer to a step, some bond breaking will be, the number of bonds which are broken will be slightly different. Using this number of bonds which are broken, we can try to calculate what is going to be the surface energy in terms of the close packed plane. That in terms of, with respect to this surface, what is the angle theta which it does? Just a minute. This is equal to the surface energy of any surface which we can consider it. Okay. This is with respect to a low index plane. So, depending upon the angle which makes the step which is created this, plus this is a low index, this is essentially a simple geometry with which it can be calculated. So, epsilon is the number of bonds which are there, A is the lattice parameter separation. Okay. If we do that, then what is going to happen is that with respect to a surface, we consider it like this, which is essentially a closed packed surface. Assume that it is a one-on-one in FCC. Then if we take any surface which makes an angle inclined with respect to this surface, the energy as a function of theta, if we consider, it has to increase whether the theta is positive or negative. That is what essentially is given there. Theta, this is positive side and this is negative side. Okay. This is how the energy is going to change. Okay. So, with a minimum which is there corresponding to where the theta is 0, that means that with respect to a low index plane. Okay. With respect to FCC, 1 is the closest packed plane. Other we have 100 plane, 220 planes are also going to be there. They will have energy which is slightly higher. That means that when we go away from closed packed plane, okay, the energy of the surface is going to increase, right. So, if we try to plot, okay, with respect to an origin, if we choose, or it could be a 2-dimensional or it could be a 3-dimensional figure also if we consider, as a function of theta with respect to, suppose we have 100 could be here, okay. Here it could be a 110 type of a plane, 111 may come in between. This is we are considering a 2-dimensional figure, okay, and this will be the normal to it is going to be a 110 type of a plane. Okay. This will be essentially 111. This is 011. Okay. This plane could, the direction could be 011 bar. Okay. This is the one with respect to which we are looking at it. Okay. Then what is going to happen is that we will be getting a plot which we call it as a gamma plot. Gamma plot is nothing but trying to find out various surfaces if a material can have, what will be the, how will be the energy be changing. Okay. The vector from origin to this surface, that is from here to here, any direction if you take it, that gives the energy. Okay. The minimum of the energy occurs along some close packed directions, correct. So, this is how a gamma plot looks at it. That means that on different directions we will have different energies. From this surface we can get some lot of information about the morphology which a material can have. Okay. Suppose we assume that a crystal is being grown from the melt. Okay. It takes some, depending upon the surface energy which is available, that is going to control the rate at which the surface will also grow. With respect to that, if we try to take it, we get some faceted surface, right. The faceted surface can always occur. Suppose we take a rod of a material, take it to or a ball of a sample, take very close to a melting point and keep it for a long time. The atom should rearrange on the surface and it should given a shape, faceted shape it should take. Or if a sample, if we take it, there is a void is there. Quite often whenever voids are there in a sample, especially it has been seen in radiation damage, when the samples are irradiated, lot of vacancies which produce, they agglomerate together and form a void. generally the voids assume a faceted shape, whereas if it is a gas which is there inside, that applies a uniform pressure, it never takes a faceted shape, it takes a spherical shape. This is used as one of the indication to tell that one. That means that internally now it tries to take a shape, a void, so that the surface energy is, total surface energy is minimum. Correct? This is what the, okay. This we can do it using what is called as a Wolf plane. That is, if I draw a vector from here to this surface, okay, draw a plane normal to this vector, okay, that is the one surface, okay, which the material can have, correct? That represents the surface, and this point represents the energy corresponds to it, because here the coordinates, if you see, these are all the directions which are crystallographic directions which are chosen, correct? Any plane normal to this vector, okay, will give, that is will give that plane, right. So, if we to this vector, if we draw a plane normal, okay, perpendicular to it, that will represent the plane 110 plane, okay. That is essentially what it is being shown. So, if we take the regions which correspond to this minimum in the cusp, okay, these are all the, and if we try to join all of them together, okay, the surface which it includes, okay, that surface is the one which it will choose to form the crystal. When it forms the crystal, this is the morphology which it will adopt. Okay. Essentially what we can do it is that from here there are so many points are there, every point I can take, okay, and find out which will be the normal to this vector, that gives the plane which it is there. When you take inclusive of all these one, the one which joins together, the minimum, if you say that with respect to area, this is the one which it will be giving rise to, others will be outside of it. Okay. That means that if we know the surface energies or the minimum in surface energy which is occurring at different planes, okay, the morphology which the crystal can have is going to change, right. That will be determined by the relative energy difference between the surfaces. Okay. Here this is a specific case for an FCC which is being considered, right. For all the samples, we are going to get a surface of similar type only. This is going to give the equilibrium shape. If a void which forms, this should have this type of a shape. Okay. This is the 3-dimensional one. That is essentially the surfaces which it has got 100 as well as 111 type of surfaces which are there, correct. The normals, if you see it, this is corresponding to 111 plane, this is 001 plane. And what is going to be the surface area which it will come, the ratio between the surface area, if we take it, of the crystal which has formed, it is equal to the ratio between the surface energies for those two planes. Okay. Okay. Before we come, what is the consequence of this? One of the consequences, if a crystal forms an FCC crystal, it can have 100 surface and 111 surfaces with which it can form. If you take a polycrystalline material, okay, and which has been heavily deformed, we anneal it at high temperature, it tries to form a grain, right. What is the shape the grain can have? This is the type of a shape the grain can also assume, because it forms with surfaces, okay, grain boundaries which are something equivalent to similar to surfaces with which it forms. Ultimate shape which it can have will be of this type with flat surfaces. Okay. This we will come to later. That is why another way in which we can consider it is if we just try to join grains of these shapes along surfaces, we will be having a polycrystalline material. Okay. Other is, so we have, so far we have talked about the type of surfaces. Okay. This is with respect to energy which we have considered. Okay. What is the equilibrium shape, okay, when a crystal is grown from a melt, okay, or it is from a vapor if we are depositing and trying to form. What is the type of surfaces which the grains or the single crystal which can have. Okay. And this we are considered on the basis of a broken bond model. This is called as. That is, the surface energy is essentially decided by how many bonds have to be broken. Correct? One important consequence which happens is that if we look here, we have considered that this is all continuously increasing and coming to a 0, another one. Is it has to be that same way? It is possible that there are some regions or some other direction for which maybe you assume this to be in this particular direction. The interface is such that the number of bonds to be broken is less compared to other regions. There could be small cusps could be occurring at different points, correct? That means that whenever we have different types of interfaces which form, grain boundaries form, as a function of angle theta, if you try to calculate misorientation, depending upon the type of nature of the boundaries, which we will come to later, we will address it in the next class, that there could be some minimum in energies which could be seen. Okay. That comes from directly from this gamma plot. This gamma plot is one important one to understand not only the equilibrium shapes which it will take, how the energy of the surfaces are, different surfaces are changing, okay. That information also we get it. Okay. Before we go further, let us look at what all types of interfaces which we can have in a material. Suppose we take a single crystal of a material. One interface which it is always going to have is surface. In addition to it, suppose the material has got a low striking fault energy. Striking faults could be produced in the material, and the striking fault, to create the striking fault, okay, some energy is required, the surface energy will be there. That is because the fault itself can be considered as nuclei of another crystal. That means another crystal is formed within this, so an interface is created. So that interface energy comes into the picture, which we call it as striking fault energy, correct? And quite often the material need not be a single element, not contain single element. It is possible that they are alloys. Okay. In alloys also, by alloying addition, the fault energy reduces. In addition to it, in many alloys, okay, at different temperatures, the concentration of the solute, that or the supersaturation of the solute is there at some temperatures, so precipitation occurs. Whenever a precipitate forms, there is an interface between the precipitate and the matrix, and this interface also, okay, depending upon the type of interfaces which we consider between the second phase, that is, suppose a precipitate which forms like this, okay, it can have with respect to this interface, that can have some energy. It can be a spherical one, that is one. It could be a cuboidal shape, it could be a plate shaped. Then there are two types of interfaces or more than type of interface, and each interface will have different interfacial energy, just like what you have on the broken bond model we have looked at it. Because of this, equilibrium shape what it will take is decided by the total free energy minimization. Okay. That is what it is going to take place. So, first an interface is created. Then what is the role of this interface? There are many roles which this interface play. As far as the mechanical properties are concerned, this interface can act as an obstacle to a moment of dislocations, correct? That is one. Then when we considered ordered alloys, we said that ordered alloys, okay, especially when the crystal structure is non-cubic, there are different variants of the ordered phase can form in a single crystal of a material, and when they come and join together the nuclei, an interface will be created between them. These are called as domain boundaries. Okay. And in addition to, there are some antiphase domain boundaries are also created. These two types, that is, one is called as a translational defect, another is called as a rotational defect. Okay. The domain boundaries are called as rotational defects because if we consider a tetragonal lattice, if one and another nuclei forms, okay, these two when they form together, the interface between them is, this is between 110 type it can be. Here this is C axis in this is in this direction, C axis is in this direction. These are two types of domains. So, this boundary is called as a domain boundary. Okay. Another thing which we considered was that one variant is there, another when there is a slight translational defect is there. This which called as that antiphase boundaries. Okay. Both the types of defects are present. Okay. These defects also can act as obstacle to the moment of dislocations. So, what is the strength of this obstacle will decide how much it contributes to hardening in the material. So, understanding these structures, the nature of these obstacles interfaces are very important. Okay. This is as far as single crystals are concerned. So, single crystals are concerned, one surface is going to be there. In addition to a surface, the type of defects which can be produced in the material. Suppose we take a polycrystalline material. In a polycrystalline material, each grain is like a single crystal, but oriented differently. The interface between them, okay, is the grain boundary. Okay. These interfaces, there are a lot of classifications are there. If the misorientation between these grains are small, okay, we call them as low angle boundaries. If the misorientations are high, okay, we call them as high angle boundaries. Okay. Even on these low angle boundaries, depending upon the type of misorientation, the classification which we use, they are as tilt boundaries or they are as twist boundaries. Similarly, on these high angle boundaries which we consider, some of these boundaries could be considered as a type of special boundaries. Okay. What are special boundaries? Suppose that boundary mismatch, when the boundary come and meet even at high angle misorientation, it should be of a particular type of an interface which they create, that it is like a low index plane if it comes between them. Then it can have very small, that is a cusp in the minimum energy, the energy could occur. Okay, these are called as special boundaries. Okay. These are what the CSL type of boundaries which we call, which we will come to later, what is CSL and all. Twin boundary is one simple example. If we take FCC twins from one to the other, the angle between these boundaries, if the misorientation between the unit cells, it is going to be very high, around close to 50 or that order. But the boundary where they meet, it is on one-on-one plane, it is an undistorted plane, that is a perfect matching is there. So, if you look at the energy of that boundary, it is going to be extremely low. you understand. Okay. So, these are all types of special boundaries which we can have. Okay. Then suppose it is a two-phase mixture of which forms the polycrystalline material, then between the two different phases there could be an interface between them. These are called as a interface. Phase interface, correct. This is also another type of boundary. Okay. All these boundaries are special boundaries which are going to act as obstacles to dislocation motion. Okay. And understanding the nature of these boundaries is very important. Okay. These boundaries could be, some boundaries could be coherent boundaries, some boundaries could be incoherent boundaries. This we will talk about what are coherent and what are incoherent boundaries. Okay. Then another way at which these boundaries are considered is that, like you look at the twin boundaries. Twin boundary is one in an FCC, one-on-one plane is the twin boundary plane. Okay. There the there is no mismatch, it is a perfect matching. Okay. If there is a slight mismatch, if you wanted to introduce, we can introduce a mismatch by introducing some dislocations into these boundaries. Okay. Any boundary could be considered as made up of introducing dislocations. That is one model of a boundary, is a dislocation model. Okay. Depending upon the number of dislocations which we introduced into the boundary, okay, the misorientations can change. Okay. That is one way to look at it. Another way to look at it, what is the structure of the boundary itself when they come and meet it. That is one aspect which we can try to look at it. Okay. Then in both these cases, okay, whether we introduce dislocations or the energy of the boundary is going to change. How the energy of the boundary changes as a function of misorientation, that is, you take one grain or a single crystal of a particular orientation, you assume that the another grain which is forming has got some misorientation. You just go on changing the misorientation between both of them and try to find out how the energy is going to change, okay, of the boundary energy which will be changing. That is one way to look at these boundaries. Okay. Then what is the way in which the energy is going to change? All these aspects we will look at it in the next class. Today what I had essentially tried to do is give an introduction about the energy of the boundaries, okay, and about the different types of boundaries or interfaces which we can have in solid samples. Okay. As I have mentioned, this is very much necessary to know about the nature of the boundaries, because that is what is going to determine, and also the strength of the boundary is important, because that controls the strengthening mechanisms in the material. Okay. What we will do is we will stop it here. In the next class we will look at the various types of boundaries.